This is my lab 2, Projectile Motion. My name is Motu Dinchasa. Okay, just for a quick intro, for this lab, obviously our purpose was to observe an object in projectile motion and compare that to both a drag and no drag computational model just to see how they compare, right? And to achieve our purpose, I basically recorded a video of a crumpled paper ball going through a projectile motion, used Tracker to get the time versus position data, created a computational model on Web Python, and then compared the two. The initial conditions for this experiment was that the object is experiencing ideal drag force in the opposite direction of velocity, as well as that the distortion from the camera is not having a meaningful impact on distances. So with these assumptions in mind, a quick preview of the results was that the ideal computation and real-life simulation differed, which likely meant that some sort of error did significantly alter our computational result. Okay, so the main physics ideas that we're using for this lab is same as the last lab in terms of Newton's second law, right? And so we're using that as well as the drag force, right, which is drag constant times the magnitude of our velocity squared times the normal vector of our velocity. And we're also using our position update formula, our velocity update formula, as well as the momentum principle. So let's just dive right into lab. So a quick overview of the experiment obviously was that the ball was thrown in parabolic motion, as you can see there, and our system being the ball and the earth. So here is the data from said tracker video where both the time and the position data were recorded. The graph below shows the x versus y in meters, where the starting point was the bottom right of the graph. And we can see that it's not perfectly parabolic, which definitely indicates that there was some sort of drag force acting on the ball. And now let's transition to the program. For the coding, I generated a computational model where the velocity was taken from the first time interval from the tracker data, and then as you can see in the code, the initial position and initial velocity were plugged into the computational model as well as the same change in time as tracker. And for our velocity and our position update, the value b, which in my case was 0.00150, was calculated by brute forcing it to find the value where the beginning and end y value correspond to each other, since theoretically this would also mean that the x values were equal at that point. And here's the code where obviously our F net is equal to our force gravity plus our force drag. Okay. Right here is the output of the coding, right? We can see the positions as the first graphs, right? The position y is parabolic, and then we can see that the change in position x isn't completely linear. Additionally, we can see that our velocity x is initially leveling off, but at the very end it looks like it is linear, which is an interesting find. Additionally, the same principle is with velocity y, where you can see that it's slightly curved in the beginning and then linear for the rest. Finally, here is the parabolic curve. Consider that the first time interval was omitted, so this is a perfect parabola, but for some reason tracker just kept omitting the first data point. Okay, so let's discuss our results. Similarities wise, they both start and end at the same value, since that's how we calculated our drag factor, and both the drag and the real life trajectories do follow close to an ideal parabola, right? But unfortunately, the computational model with drag reaches a lower x displacement, while the one without drag reaches a greater x displacement, which means that the values are not identical and there is some margin of error. And we can see in the graphs, looking at the x direction, that the drag x direction obviously went less in the x real life. And then we can also see in our y direction that that the y drag and the y real were completely identical, since that's how we set it up. And so considering all this, we're seeing that choosing to line up the y values in the computational model led to a mismatch in the x values. And so this indicates that the assumption that drag is acting ideally is wrong, and that there are potentially some error sources contaminating the data. Okay, so what if the object was initially thrown up with the same speed? Then it would take longer since the force acting on it would be the same by gravity, and the drag force would be completely in the positive y direction, so it would take a longer time. And what does it mean? Do any of these models predict terminal velocity? Obviously they don't, but we could test terminal velocity if we drop something from an extremely high location and find where the velocity starts leveling off. So some error sources are the camera movement during video recording, distortion of an iPhone camera, terrible scale that likely led to an incorrect mass for the pampered wallet, as well as the human imprecision using tracker. And so to conclude, the results show that the ideal is very close to mimicking the behavior of the real life object, but not completely. Thank you.